In acoustics, you can check the possibility of a constant pressure mode, which corresponds to a rigid body mode in structural mechanics, by looking at the determinant of that acoustic pressure matrix or stiffness matrix. When we do that, we find that the determinant of the matrix is 0. That means it's singular, and that there do exist 0 eigenvalues to this dynamic problem that we pose below. In this case, there will be one such 0 frequency corresponding to an elevation and pressure uniformly over the element. When we do pose the dynamic equations of motion here, with both this stiffness and inertia term, we get this form. It's natural to bring out an eigenvalue lambda defined here in terms of the wave number. And from this, we're hoping now to solve in a formal way this eigenvalue problem. It's in the standard form, it turns out, when we choose to not allow volume flow into any of the 3 nodes. And that corresponds to an element that has rigid walls and doesn't permit flow in or out of the boundaries. Therefore, none of the 3 equivalent nodal volume fluxes will have any value. They'll all be 0. So that leaves us with the unknowns shown here of the 3 nodal velocity potential terms. Our goal is to find the eigenvalues of this general eigenvalue problem, and the eigenvalues themselves will be related to the frequency of vibration of that mass of air contained within the triangular element. Then the modes, or the mode shapes, are going to be the pressure fields basically throughout that same element, and give us some idea of how the fluid is packing against one wall when it's under compression, or moving away from the wall when it's in a rarefaction. And we'll see that in a minute. Here is the equation of motion again in a form with the eigenvalue shown. You combine the terms and you have this form of the equation, something like a dynamical matrix here on an eigenvector, and basically you're mapping the eigenvector into the 0 vector. The condition that you can do this is that the equation here is singular. The set of equations is singular, and you check that by the determinant of the total dynamical matrix here on the left. When you set that to be 0, there's a common factor of lambda outside, which shows that there's 1 0 frequency involved. That's that constant pressure mode. But then, using the quadratic formula, you find 2 other frequencies given here. They come out in simple ratios 1 and 3, and then we can interpret that in terms of frequencies in the next figure. We recover the frequencies of vibration from that eigenvalue, and that's done here. Then putting the frequencies closer and closer to a final numerical form, we express it in terms of the lambda, and then we get this form. Finally, we substitute the actual eigenvalues of the problem that we found, the 0, the 1, and the 3, and then we recover, and then putting in the proper other constants here. We put in lambda 1 is 0, call it the lowest, which is a 0 frequency, and then you get 0 here. Lambda 2 had a unit value, which is put in on the right side here, and that gives you 18 hertz. Lambda 3, which was a 3 value, gives you roughly 32 hertz. So those are the frequencies of that entrained air inside that closed triangular box. So we now have the frequencies, roughly 0, 18, and 32 hertz. Now, to what kind of a velocity and pressure distribution do those correspond? Well, we find the eigenvectors to do that. And by the way, the method that we just used for a single element is called the determinant method for finding the eigenvalues. That's actually pretty old-fashioned nowadays. That's not used so much. It's only valid for small problems. When you use the determinant method to find the eigenvalues, then you can substitute back in and find the eigenvector terms by elimination, by a Gauss elimination sort of a procedure. Here I write out the equations for the lambda 0 case shown here, and you can solve these simultaneously by taking equations 2 and 3 and working with them, and you'll get that phi 2 is the same as phi 1, and then finally phi 3 is the same as phi 1. That gives you then a vector, an eigenvector, the first one by this subscript outside the curly braces, an eigenvector that has the same value in each component. We normalize that arbitrarily to have a unit value shown here, and I show it as this elevated surface where phi is above the xy plane and shows these phi values. Now, the closest thing we could easily approximate that to is a pressure field. So, and there's some complex relation there, but it's good just to think of it as pressure. And you see that what you have then is the equivalent of a small pressure induced into that chamber, and which raises uniformly the pressure in the entire chamber. And it's a degenerate vibration at 0 frequency. For the second mode, we'll do something similar by putting back the eigenvalue lambda equal to unity and putting it into the acoustic pressure matrix or stiffness matrix, looking for a 0 determinant of that matrix, and what we get is this form here where phi 2 and phi 3 are related, in fact in an inverse way with a minus sign. The second equation can be worked on to give phi 1 is 0, and that means that you have a pressure field normalized here with 0 in the first term and unity in the second, minus unity in the third, and it's kind of a teeter-totter shape shown here for the pressure field. Now what that really means is that you've got a wave traveling along this long dimension of the element along the hypotenuse. It's actually angled in this view here. It's a little hard to see, but then the air will on one half of the cycle compress in this side, and then on the next half will compress on the far side. Since velocities go like derivatives of this function, you do have a bit of a paradox where there's a mismatch in velocity at this boundary. And that's something that mismatch is something that we've hoped to minimize with the Glurkin method. That error is a part of the approximate nature of this particular body. You'd wonder how can the fluid pass through the wall if it has a velocity there, but if you look into the theory, you find that that's not an exact boundary condition in this problem. Nevertheless, that frequency then of roughly 18 Hertz is about what the wave speed is for a wave basically traveling the long dimension of the element and then rebounding and ultimately setting up a standing wave because of its sister wave going in the opposite direction. And then these are the pressure magnitudes. Let's now look at the third mode and find the pressures at the nodes in that case. There we have lambda of 3. We put that into this dynamical matrix, finding this reduced matrix numerically. Then the question is, can you find phi 1, phi 2, phi 3? Now the determinant of this is going to be 0 if you check it out. And that was a condition by which we originally found the lambda to be 3. This time we do have to solve simultaneously with equations 2 and 1 being subtracted, and this time you get that phi 3 and phi 2 are the same. The equation 1 is combined with equation 3 to get this value that phi 2 is half of phi 1. And adding those results, we get the third eigenvector shown below here. That doesn't tell you very much. You need the figure shown over here to see what it is. Notice that this time we have a unit height on the origin there where the one corner of the element is, and then along the hypotenuse you only have the minus 0.5 terms. What that does is establish a nodal line in the Chladni sense, a third of the way across here, and I have to project that into the xy plane and find the intersection. And that means that on this particular half of the cycle shown, you've got the fluid rushing to the left and compressing against the origin here. And then on the opposite half of the cycle, the fluid would return to the other direction, causing actually a focusing effect at the point over here and giving higher pressures by a factor of 2 than when it rushes to the other side and rebounds. So it's an interesting focusing idea. This time we're finding what we're basically getting in a top view is the frequencies in a closed container where the fluid is rushing back and forth perpendicular to the longest dimension, which is the hypotenuse. And so this would naturally be a higher frequency because it has the shortest wavelength that you might propose for fluid to move in that chamber. It's instructive now to do a sanity check on this set of results for frequencies. I think we've already got a sanity check on the mode shape because it seems to make sense, but we'll talk about those as well. Certainly starting with the constant pressure mode, that's a physically realizable sort of situation. One way you could idealize that situation would be if there was a small puff of air put into the chamber and then the opening was sealed. That would uniformly raise the pressure in the chamber and then it would stay there. Since we have fixed boundaries here that are reflective sealed boundaries. Now, of course, this takes a small perturbation to imagine that, and that's always done in the sense of an eigenvalue problem that you have to assume that there's some event that would cause the eigenvector to oscillate. But once it's started, it maintains itself. In this case, the constant pressure field maintains itself. And I like to think of it as an oscillation with zero frequency. I'll plot the pressure field in the second mode in the next figure. It's shown as the shaded surface here. If you imagine that in the opposite phase, where the pressure is reverse sign, then there would be a surface that would pass in this manner. And then there would be a Chladni nodal line along this direction from the origin out to the middle of the hypotenuse, and that would be a line on which pressures would stay zero. Currently, with the phasing shown at time 0, the red surface given here, there would be a positive pressure along the near face and a negative pressure on the far face. With this pressure field, it would tend to make the velocity then move particles away from the near wall in this direction. Let's concentrate on the pressure field on that cut edge of the hypotenuse, and I'll do that in the figure here on the left. The opposite phasing in time would give the dashed line, which would be the pressure reversal. One way to look at this would be to say that although we're interested in the pressures within this closed chamber, which is our triangular element, that actually by mirror images we could extend that pressure field outside the walls into neighboring mirror image elements. When we think along those lines, we realize that what we're trying to do is predict a pressure field that's actually a sine wave. I probably won't draw it very well here. And that what we're really trying to get is a zero slope to that pressure field at the wall. If I plot below then the velocity, which would be the derivative along the hypotenuse direction, I would get the square wave shown below. And this brings up the paradox then that you have the jump in velocity at the wall. So there's a discontinuity in the velocity boundary condition. That's okay, however. To argue that, you almost have to go into some energy concepts and show that there's no energy lost by that jump. But we can take that on faith, and it's also found in the Turner constant strain triangle in structural mechanics, where you get a jump across the inter-element lines in strain and ultimately in stress. I'd like to make a side argument now about how standing waves are in fact created by two traveling waves in opposite direction with the same speed. So we'll do a mental experiment shown in the three figures below. First, at time 0, let's imagine that there's a red wave shown here which will travel to the right with speed c, the speed of sound. There's also a blue wave that will travel to the left at that same speed. They're meant to be coincident, but I've slightly offset them so you can see the different colors. We're plotting the field variable here, which is the pressure field. The characteristic length that we're interested in corresponds to L here, the distance between our two rigid walls, say in our triangular finite element. At a time later, delta t later, which we'll take to be L over c, that would be just sufficient time for the point, say, on the red wave at its peak to move over one characteristic distance, which I've shown in the second figure here. Likewise, the blue wave will move one characteristic distance L to the left. At this point, the two traveling waves reinforce each other again, but with opposite polarity from the top figure. You can also see that this will constitute a half period in time, because if we do this experiment again and look at 2 delta t, you will see then that the waves reinforce with their original polarity. And so that constitutes a return to the original position and what we mean by a full cycle of motion. We can then construct what we call a frequency here, which would be 1 over that period. And I can just sketch it here right on the drawing, that frequency would equal then 1 over the period. Well, the period we're talking about now is 2L over C, so it would be C over 2L. That's not really obvious, and I think you have to sit and think about this a bit. And we'll carry forward, though, this concept of how you get a standing wave frequency from a traveling wave speed of sound and characteristic distance. I'll write down that formula again for the frequency here. And the thing to remember is that in a closed chamber with two reflecting walls, the longest wavelength possible is really twice the length of the distance between the two walls. And so that this is the frequency for a closed chamber with two reflecting ends that are distance L apart. Another fundamental idea of what we've just discussed is the accuracy involved in using straight line segments to interpolate what really is a sine wave. And by now you see that what went on between the two walls, which we mentioned here with vertical lines, is really a half of a wave. And if you fill that in with the full sine wave shown here, you now see what it means to have violated the velocity condition at the wall. Means that you have this peaked representation of a sine wave. A related question then would be, how many of these straight line segments should you use to represent a full wavelength? And that's often the way that it's given, is going a full wavelength. And people often say that that's a minimum of 5 elements. Electrical engineers sometimes are willing to go with fewer representations on straight line segments because a lot of their measurements are logarithmic, and we have a little bit of that in acoustics as well because of the hearing physiology. So people get by with a modest number of straight line segments. In some forms of structural mechanics on stress, you might rather have 10 such straight line segments representing something that were a sinusoidal stress field, let's say.